Hello, my name is Khairallah, and I will be presenting Camel Morph MSA, a large-scale open-source morphological analyzer for modern standard Arabic, developed by the Camel Lab at New York University, Abu Dhabi, as part of the LREC-COLING 2024 conference. Over the last 4 decades, many approaches have been explored in developing Arabic morphological analyzers and generators. These tools continue to show value for Arabic NLP when paired with state-of-the-art neural models on various tasks. But developing such tools is neither cheap nor easy, and many of them are either not open source, not freely available, or incomplete. In this presentation, we showcase Camel Morph MSA, which is part of the overarching Camel Morph project, a large effort to develop morphological analyzers and generators under a common framework for a number of Arabic variants, namely Modern Standard, Classical, and Dialectal Arabic. The result is a very large analyzer with over 100,000 lemmas, producing around 1.45 billion analyses for about 535 million diacritizations, almost an order of magnitude larger than the baseline. It is easy to extend and edit and allows for seamless integration of new lexical units. We also benchmark our models against publicly available morphological analyzers and make all our resources, code, guidelines, and documentation publicly available through the following link. Camel Morph MSA is developed within the Camel Morph framework, which relies on a two-step process to perform morphological analysis and generation as seen in the following diagram. The first step requires designing morphological specifications, seen on top, describing the language's grammar and lexicon in a manner which is annotator-friendly. These are then converted via an offline process powered by its DB maker algorithm into a morphological database in the 6-table style of the Buckwalter Arabic Morphological Analyzer, or BAMA for short, databases. The created databases can then be used by any compatible analysis and generation engine, like Camel Tools, for example. The morphological specifications can be divided into an open class lexicon specifications for lemmas and stem, a closed class morpheme lexicon, or morph for short, for affixes and clitics, and order specifications. Morph, lexicon, and lexicon consist of allomorphs organized into morphemes. The lexicon is a large repository that contains stems, their associated lemmas, and other features. And finally, associated with each allomorph is a set of handcrafted conditions which control the allomorph selection of specific morphemes. The offline DB maker process makes heavy use of these conditions in the morphotactic validation process to determine proper combinations and compatibility among the allomorphs in a word. Finally, and denoted by the regex mapping rectangle, the framework accommodates the use of orthophonological rewrite regex rules as part of the specifications, such as sun letter handling in Arabic or epenthesis, to be used by the analysis and generation engines. Now, we make 2 extensions to the Camel Morph framework, as seen in the green color. The first extension, called category factorization, reduces redundancy by mapping categories with the same dependencies, thereby speeding up online analysis and generation. And the second one allows the framework to accept scripts that pre-process specifications before they are provided to the database maker. This feature is particularly handy when specifications can be automatically generated without human intervention. Now, the morphological specifications are divided into essential and supplementary elements. Essential elements, crucial for the morphological modeling, include order specifications, morpheme class, lemma, stem or morph form, functional and form-based features, along with required and set conditions, while supplementary elements, not shown here, provide additional dependent information to match the performance of other systems and automatically extend essential elements when necessary. And these include root and pattern information, transcription, tokenization and segmentation, English gloss, and lemma likelihood information. In developing CAMELMORPH MSA, we use manual and automated techniques to extract, build, correct, and validate specifications. We manually specified affixes, clitics, sequence orders, and morphological conditions for MSA and potential dialectal Arabic modeling. For the lexicon, we automatically extracted and manually adjusted from sources like Kalimastar and Wikidata to fit our specified morphological conditions and to cover full morphological paradigms. And given the size of this project and its many moving parts, we regularly quality checked our specifications using a number of techniques that isolate specific phenomena while freezing some elements such as the lemmas or POS, part of speech. Specifically, we worked on debugging the morphotactics of the affixes and clitics, lemma paradigm completeness, and stem sub-paradigm correctness. We regularly made use of the Camel Tools generation engine to validate the analysis and generation processes. And we used different clustering techniques to group related phenomena into size manageable sets for our annotators to debug. The process usually involved the assigned annotator marking wrong outputs and discussing them with the rest of the team to make the needed changes. All markings of wrong and correct outputs are banked so they can be used in later automatic progress evaluation. In the bottom right table, we show 3 lemma examples that summarized most of the framework's components, where the shared colors between the tables and diagrams denote corresponding parts. In the morphology specifications row, we see the morpheme classes in order, as per our defined order sequences. The counts pertain to the number of specifications per specified unit that participate in the number of unique analyses that can be generated for that specific lemma, seen in the bottom row. After the specifications are converted by the DB maker to DB entries, note how a relatively small number of allomorphs is mapped into a large number of complex morphemes in the DB section below. In particular, the buffers, which are small segments meant to complete other morphemes under different morphological contexts or conditions, together with the passive voice scripts mentioned earlier, reduce the total number of stems that annotators have to manage at the specifications level. 10 generated from 3 specified for the verb, and 4 generated from 2 specified from the noun, for the noun. Finally, constrained by the compatibility combinations, the complex morphemes can combine into a very large number of analyses. In terms of evaluation, the left-hand side table compares the statistics of our specifications, marked as CAMELMORPH MSA specs, and their associated database, namely CAMELMORPH MSA DB, with those of the SAMA/Kalima database, henceforth Kalima DB. We first note in sections A and C the 10% increase in the number of stems between our specs and database. This shows that the specs are able to compactly represent stems, denoting a more annotator-friendly morphological modeling, and is attributed to the buffer system, which shifts the modeling weight to morph from lexicon. This can also be seen at the prefix and suffix condition and order levels in sections B and D, where a small number of specifications leads to a large number of sequences. We also note that the number of lemmas and stems for our database is about 2.3 times greater than for Kalima DB. This is due to two main reasons. First, the gaps of verbal paradigms we filled by adding command and passive voice stems, most of which were absent in Kalima. And second, the 62,000 mostly undiacritized Wikidata entries, which we identify as proper nouns annex in the table. Finally, the number of analyses that our database can generate is almost 9 times greater than for KalimaDB. And this is reflected by the greater number of compatibility combinations and complex prefixes, suffixes, and stems. The number of unique analyses when clitics are not considered is about 8.1 million for our database, or 3.2 million without the proper nouns annex, versus 1.5 million only for KalimaDB. This shows that despite the high inflation that clitics may cause, our generative power is still superior with and without the annex. This large increase when including clitics is due to the modeling of various less frequent classical Arabic morphemes in modern standard Arabic that are not modeled completely or simply not modeled at all in KalimaDB, like the interrogative proclitic, the energetic moods for verbs, and the indirect object pronominal clitics. Furthermore, we conducted a speed experiment in which we note that it takes about 45 minutes to compile our DB from our specifications, and then we are about 2.5 times slower than the KalimaDB in online analysis and generation runtime. And that is due to our database covering more morphological ground. On another hand, we conducted some recall experiments against the training portion of the Penn Arabic tree bank, in which we were able to recall almost 96% of all word analyses. Of the remaining unmatched 4%, 90% are basically due to gold errors in the tree bank, according to a manual sample analysis we carried out, where we actually model more consistently. We also conducted a coverage experiment over a very large 10.6 billion word corpus, noting that we have 10% less out of vocabulary for the MSA portion of the corpus in type space, and 20% less out of vocabulary for the classical portion, also in type space. Manual examination of out of vocabulary types shows that proper nouns seem to carry the bigger share of out of vocabulary. Other major sources of out of vocabulary include spelling errors, spelling variations of the same word, and erroneous merging of words. These results show that paradigm gap filling, the addition of Brer phenomena, especially the energetic mood and indirect object pronominal clitics, and the seamless integration of Wikidata entities had a considerable impact on out of vocabulary reduction for us. We presented the largest open source Arabic morphological analyzer and generator to date, and evaluated it against a popular morphological analyzer, showing superior performance. In the future, we plan to continue expanding CAMELMORPH MSA to increase its coverage further, to include more MSA and classical Arabic lexical items, as well as expanding it to include Arabic dialects. We plan to continue filling any gaps in the database, such as any incomplete diacritizations, transcriptions, and missing glosses. We also plan to increase its robustness to input spelling errors and develop smart back-off utilities to allow it to propose plausible answers for unseen words. We also plan on improving speed performance and offering users options for controlled, reduced database sizes. Thank you very much for your attention and have a nice day.